The figure here shows a simple braking mechanism. Consider a wheel that is spinning counterclockwise as indicated. And the braking mechanism consists of two parts that I call part 1 and part 2. Part 1 is pinned to a solid frame at point P. These two parts, that is part 1 and part 2, are pinned together at point Q and connected by a spring. When the operator pulls down as indicated over here, the mechanism presses part 2 against the spinning wheel. That rubbing action causes the wheel to slow down. Now what I want you to do for me is to draw two free body diagrams. One free body diagram for part 1 and a separate second free body diagram for part 2. Notice I'm separating these two parts out. This is what the problem calls for. So in case you're having some difficulty sort of wrapping your mind around what is happening here with this mechanism, I mocked up a little simulation of this thing. More or less the same thing. It looks a little rough, but let me show you what's going on. So click the play button, and this thing is, you can see it's a dynamic system, right? You got the spring wiggling around, and yeah, so this thing moves, right? So I got part 1 in the sort of light blue and part 2 in the pink. If I pull part 1 down with my hand here, part 2, the pink one, comes in contact with the wheel. The wheel's not spinning at this moment, right? So by pulling this part 1 downward, I can get part 2 to squish a little harder into the wheel. So let me get the wheel spinning. As I said in the problem, there it is, spinning counterclockwise. And if I pull it down, these two parts rub together and it slows the wheel down, right? So that's the braking action, right? See, one more time, there it goes. And by tugging this down here, these two parts rub together and I apply braking action to the wheel. Yeah, cute, huh? All right, so our objective here is to draw forces onto these parts. So let's remind ourselves what a force is. A force is a push or a pull acting on the object. Furthermore, forces have a direction to it, right? You can push left, pull right, up or down, whatever. So forces are vectors. And another thing I like to point out is that forces are interactions between bodies. They're bodies pushing or pulling on other bodies. I like to remind myself of these three essential elements of what a force is when I'm drawing free body diagrams, because it helps me think this thing through. All right, so as I do this, I think I'm going to draw the free body diagrams from both bodies at the same time. So the first thing, I like to start on some easy pieces. Let's start with the weight. Weight always seems easy. You know, I told you these things had centers of gravity, so that indicates that there's a weight. And the weight is always pushing down towards the center of the earth. So I'm going to put a weight on part number 1 and also weight on part number 2. Again, weight acts, if we have a body with distributed mass, the weight acts through the center of gravity. This is something you should have learned in your statics class. And of course, so there's my two weights, both acting straight down, both acting through the center mass. And of course, I need to label my forces, so I'll call this one weight number 1. And this other one I'll call weight number 2 for part number 2. Now remember, I always label my weights, so I give them a symbol, in this case W1, W2. But since these are vectors, right? Forces are vectors, that means I have to label them as vectors. I have to put the little arrow over the symbol or some sort of other reasonable thing to indicate that this thing's a vector. All right, weight's done. See, it's not too bad. Why don't we put in the spring here now? So remember when we pull down on part number 1 over here, remember what happens? Part number 2, if you recall, or maybe you can just see it right here. Part number 2, as we pull down on part number 1, part number 2 is going to rotate clockwise, and that's going to stretch the spring. Does that make sense to you? Another way, we can go back to the simulation if you want. So here was this thing. As I pull down, right? As I pull down, that spring gets a little bit longer, right? Therefore, I'm thinking the spring is in tension, right? The spring length is a little bit longer than its natural length. In that case, the spring is pulling on part number 1 directly to the right, and it would be pulling on part number 2 directly to the left, like so. These two forces are in these forces are in exact opposite direction. Actually, in this picture up here, it looks like both, since the spring is oriented horizontally, these two forces should be horizontal, right? At least in the configuration indicated in the picture. What's really important is, since the spring is a two-force member, the forces on the ends of the spring have to be in exact opposite directions. Otherwise, this two-force member, the spring with just two forces on the end, it could not be in equilibrium. This is something you should have learned in statics. So this is really important. When we have a free body diagram, we indicate how the forces, especially when we have a force between the bodies, we indicate how the force interacts on each individual body, and typically they act through what looks like Newton's third law, right? These two forces have the exact same magnitude and they have exact opposite directions. And I have to label them. I'll label the top one S, and it is a vector. So there we have that one. And then the next one, it's also a spring force, right? It's the same exact force, just in the opposite direction. The way we indicate that is we have the exact same label, but since it's in the opposite direction, we call it minus S, right? If I negate a vector, right? If I have some vector, it's pointing in some direction, the negative of that vector is pointing in the opposite direction. So our labeling, it's representing Newton's third law. All right, so the next thing I want to do is review what happens at the pin joint. We have a pin joint here at point P. And I don't know, let's just think about this for a moment because some people seem confused. So what I have here is a little sort of makeshift pin joint that I just created. I sort of bolted two small pieces of wood together right here with a little bolt going through there. One important thing to know is that these two members here are just free to rotate about that pin joint. That's why we call it a pin joint. It's just free to rotate there. So there are no moment actions acting at the pin joint, none whatsoever. Both objects are free to rotate, or any object pinned to another object is free to those objects are free to rotate about that pin. All right, no resistance whatsoever there. But what the pin does do is it enforces a constraint. It keeps these two holes through the objects aligned with each other, right? So if I move one of these objects left and right, the other object pulls back left and right, right? So this pin provides forces left and right, which prevents relative motion left and right. And I've purposely made my hands pliable here so it does move, but if they had perfectly rigid pin joint there, it would not move left and right. Also would not move up and down either, right? So here's me trying to move these things up and down. Again, the pin, provides a push or a pull to prevent these two things moving left and right or up and down. And really, up and down, left and right aren't important. They could be at 45-degree angles, right? The important point is that the force between these two pieces are somewhere in the plane here in magnitudes that are necessary to keep these two objects from moving relative to each other, right? That's what the pin joint does. So when I see people write the forces from the pin joint, a lot of times what people do is as follows. One draws horizontal vector and a vertical vector acting on these things. Two different forces, one in one direction, another one in the perpendicular direction. That's perfectly fine. Absolutely fine to do that. I just kind of sort of prefer to just draw a more or less arbitrary force on this thing. So here's what I'm going to do. I'm just going to draw. Here's my force acting on the pin. Let's say it goes this way. I'm not sure exactly which way it goes. But I'm going to choose a force which is obviously not perpendicular to this part number one, or parallel to this part number one, or whatever. This is some force in the vertical plane here that presumably we would need to solve for if we were to completely do a complete analysis of this object. But again, I'm going to give it a name. Since it's a force acting on pin P, I'll just call it P. Again, it's a vector. And likewise, there is this other pin joint, right? At Q. This is pinning the two objects together. But nonetheless, it's a pin joint again, right? So this should be another force acting over here. And I'll call this force Q. How's that look? Yeah, incidentally, I can go back to the simulation again. I like this thing. I have to play first. Okay, there we go. Check it out. It's moving. Look, here's the force on the pin right here. Yeah, let me bounce this thing a little more. Woo! So there's the force on the pin, right? You see it's really actually in the same direction that we just drew ours in. And likewise, here's the other pin. This is the force on part number 1. Yeah, so there's the force. It's not perpendicular or parallel to any particular object here. It's just sort of in whatever direction is necessary to keep these keep the bodies pinned together, or this other body pinned to the wall. Notice it's also showing the spring forces too. Isn't that cool? We got it exactly right. Yeah, this is exactly what we drew. I love looking at this thing. Simulations are really cool. All right, so let's come back to my free body diagram. So here we are at point Q, or pin Q, on part 1 that had a force going this way. I kind of like that picture. But remember, forces are interactions between bodies. So if I have a force on my free body diagram for part 1 coming from part 2, then I should have an equal and opposite force on part 2 coming from part 1, right? That's Newton's third law. That has to be reflected in our free body diagrams. So let's put this in here. I'm going to try to draw this. So equal in magnitude, opposite directions. That looks pretty good. So if Q is the label for that force on part 1, then the force on part 2 is exactly equal and opposite, so I'm going to call it minus Q. Like this. Wow, these free body diagrams are starting to come together, yeah? Let me do another one. The operator's pulling this end of part 1 downward, right? That's a force on part 1, so we put it on the free body diagram for part 1, so let me do that right here. At least in my mind, I'm picturing the operator's hand pulling this part downwards. So I'm going to call this vector H for the operator's hand. And let's take stock of where we are. So I'm thinking I've cataloged all the various different ways things are pushing and pulling on part number 1. So I'm thinking part number 1 is done. Next, I have to go to part number 2. What's going on with part number 2? Again, I have the spring, I have the pin at Q, I've got the weight. But we got one more thing going on. Notice that part 2 is in contact with the wheel. So I need to put some forces on there too. So again, we usually break this up into 2 pieces. So the first piece is what we call the normal force. The first piece is the piece that prevents this part number 2 from penetrating the wheel. Right? To keep part 2 from penetrating the wheel, there's going to be a force perpendicular to that surface of contact. So I'll call that N. Now, if these 2 objects were perfectly slippery, right? If they're coated in grease or something like that, that would be my only force. But they aren't coated in grease. In fact, the whole purpose of this brake is to slow the wheel down, right? So there's going to be a friction force that's tangent to the surface here. A friction force that's due to the fact that these 2 surfaces are rubbing against each other. So in this free body diagram, let me try to sneak in a vector that's tangent to the surface. So the next question is, which way does that friction force act on part 2, right? We're drawing a free body diagram of part 2, not the wheel, part 2. Which way does it act? Does it act down and to the left or up and to the right? Think about it for a second. The best way I like to think about this is just embody it. Just imagine that force. Imagine instead of having part 2, what if you put your hand against that spinning tire, that spinning wheel? If you were to put your hand right there instead of part number 2 here, since the wheel is rotating counterclockwise, I hope you realize that this force from the wheel acting on part 2, or from the wheel acting on your hand, if you want to make that a substitute, it'd be acting down and to the left. And guess what? Now we've done it. I think we have the entire free body diagram of these two parts. So finally, what I'm going to do is work out a little bit of vector decomposition. I'm going to take these forces on part 2 down here, and I want to resolve them into components that are in the E hat 1 and the E hat 2 directions as defined in the top left picture, where E hat 1 is sort of tangent or parallel to part 1 and E hat 2 is perpendicular. Notice that part 2 is at an angle theta relative to the horizontal as I've depicted here. So let's just dive in. So I'll start with the easy ones. Let's start with let's say the normal force. Now again, by definition, the normal force is perpendicular to part 2, right? So normal force must be in the E hat 2 direction. Actually, as I've drawn it, actually has to be in the minus E hat 2 direction. So I'm going to say this is scalar n minus E hat 2 direction. Here, this scalar n is, let's call this the magnitude of the normal force. Okay, so scalar n is a positive number, or at least it's a non-negative number, right? So if I have a positive n here, so I have a minus positive n E hat 2, or positive n in the minus E hat 2 direction, this is going to be a force. It has to be a force sort of upward and to the left as I've drawn in the free body diagram. Next, let me put the friction force in. I'll do that in purple, I guess. Friction force, I'll call it, so this one's tangent to part 2, so it's in the E hat 1 direction. In fact, it's in the positive E hat 1 direction as we've defined it up top. So I can call this one F E hat 1, where the scalar F is the magnitude of the friction force. Right? When we have this sliding friction, kinetic friction, that means we know which direction the friction force is in. It's the one that opposes the relative motion between the two objects. So we argued before that friction force has to be sort of downward and to the left, or in the positive E hat 1 direction. So next I'll tackle the pin force, which I called Q. Actually, the force that's acting on part 2 I called minus Q, so I want to call it that. What is this? So I've drawn it in some direction, but I'm not sure I got the direction exactly right, or even remotely right in general. So what I really want to do is just write this as some more or less generic force that has both E hat 1 and E hat 2 components, because that pin force generally has both components. So I'm just going to call it minus Q1 E hat 1 minus Q2 E hat 2. So this is just a generic force that's in the plane of the body here, and it'll be up to the physics to determine what the Q1 and the Q2 are. The important part is that it has to obey Newton's third law. So I can say where positive Q, the force acting on part number 1, this is going to be positive Q1 E hat 1 plus positive Q2 E hat 2. Right? So that's how I'm going to decompose that force on the pin. So those are the pretty straightforward ones. The next two are less straightforward. We're going to have to do some trigonometry. So let me clear off some space. So the first is the spring force acting on object number 2. So the spring force, I'll just have it written on my free body diagram already. I'll just write it again over here because I want to make a vector triangle. So if I take S, or in this case really minus S, and decompose it into components in the E hat 1 and E hat 2 directions, then what do I get? So here's S. This would give me a piece in the positive E hat 1 direction and in the negative E hat 2 direction to combine to give me the spring force. So this is my vector triangle. Next thing I do is identify an angle in that triangle. And that angle down here is theta. It's the angle between horizontal and part 1. So the angle theta is right there. Right? Now that I've have my geometry all worked out, writing the decomposition is fairly simple. So I say minus S, or that spring force, is going to be, well, I got this piece right here, which is in the E hat 1 direction, or I should say positive E hat 1 direction. So I'll call that S. And that's the adjacent side of the triangle. So S cosine theta, E hat 1. And then I got this other piece, which is in the minus E hat 2 direction. So I'll say minus S. And it's the opposite side of the angle in the triangle. So I'll call it sine of theta, E hat 2. There's my vector decomposition. And this is, so if S is positive, that means the spring is in tension, just like we assumed in this problem. That'd give you a spring force to the left acting on part 2. And if S happened to be negative, S can be negative in this case. I guess the spring could be in compression, at least in principle. In that case, it would just flip everything around, and the spring force would be to the right. That's what you get by changing the signs of both components. All right, so there's my spring force. Finally, I'll work out the decomposition for the weight acting on body 2. Again, this weight, which is vertically downward, is going to have components, it looks like in the positive E hat 1 direction and the positive E hat 2 direction. So let me work out the vector triangle, or force triangle. Here's the weight vector acting straight down. Then it's got a piece in the positive E hat 1 and a piece in the positive E hat 2 direction. Like so. So let's identify an angle again. Let's just go back to theta, just the definition of theta. If I draw a horizontal line right there, then theta would be this angle right there. And a little bit of playing with angles and triangles, it would tell you that this is equivalent, or it's the same angle as this one down here in the triangle. Given that, our decomposition is now some simple high school trigonometry. Right, the piece in the E hat 1 direction is opposite of the angle theta. So I'm thinking this is W2 sine theta, E hat 1. And the piece in the positive E hat 2 direction, this one down here, is adjacent to the angle theta, so this would be W2 cosine. And here, the scalar W2 here is what I'm calling the magnitude of the weight vector, right? And that wraps up our exercise. I'm going to end it right here.